Hello friends, today I will discuss the phasor diagrams of transformer. So here there are two types of phasor diagrams on the transformer. One is by neglecting the leakage impedance of the transformer, the other is by considering the leakage impedance in the transformer. So phasor diagram with the pure resistive load, inductive load, capacitive load without a leakage reactance means negligible resistance also present. Similarly, the phasor diagram with resistive load, practical inductive load, practical capacitive load. Before we discuss these two phasor diagrams, so let me consider first phasor diagram of the transformer under no load condition, that is also occurred without load. And if you draw the diagram, that will be like this. This is the magnetic core, and on one leg of the core there is a winding, and this winding is connected to the AC supply, and this winding is becomes what is called primary winding, and the secondary winding is placed on the other leg of the core, and this winding is called the secondary winding. The definition of primary winding means the winding of the transformer connected to the AC supply is called the primary winding. The winding connected to the load or without load or open circuited is called the secondary winding. So once the AC supply is given to the primary winding will draw the current called I naught under no load condition, and this I naught will establish flux in the core like this phi, and this flux links with the primary winding, and due to this there is a induced EMF in the primary, that is called E1. Similarly, there is induced EMF in the secondary winding also due to this flux linking. Then if you draw the vector diagram for this, the applied voltage here we call as Vp or V1 will produces a flux called phi m, which lags the Vp by 90 degrees like this. This happens due to the no load current I naught. And this no load current will have the two components. One is called magnetising component, which is in phase with the flux, whereas the other component is called the coreloss component or active current component IC, which is in phase with the Vp. And because of this flux, there is induced EMF in the primary winding called E1 or EP, lags the flux by 90 degrees. Similarly, the induced EMF in the secondary winding is called ES, that also lags the flux by 90 degrees, so that EP and ES are in phase, but they are lagging behind flux by 90 degrees, but they oppose the applied voltage Vp or V1. And the angle between IC and I naught is called the power factor angle, and I naught is the vector sum of IC and IM. So from this vector diagram we can write cos phi naught as IC by I naught. Similarly, sin phi naught we can write IM by I naught. So cos phi naught is equal to IC by I naught. From this we can write what is called IC, that is I naught cos phi naught. Similarly, no load core loss we can say Vp into IC. So this is measured by the wattmeter connected in the circuit. Then this IC can be replaced with I naught cos phi naught. So similarly, sin phi naught means Im by I naught. From this we can calculate what is Im, that is I naught sin phi naught. So once we know IC value and Im value and the applied voltage or induced EMF in the primary, then we can calculate what is the no load equivalent circuit, that is nothing but V naught, and the current here is I naught, and their components are Im and IC, and this R naught can be calculated using the V naught by IC value, and similarly X naught can be calculated using V naught by Im value. So once we know V naught by Im means X naught is known. So this is the equivalent circuit for the no load condition of the transformer. We need this while drawing the vector diagram for different load conditions of the transformer. So let me consider first the phasor diagram of the transformer without leakage reactance and with pure loads. So before we discuss that, so let me draw the equivalent circuit of the original transformer like this. This is the primary winding equivalent circuit. This consists of applied voltage V1 and R1 is the winding resistance, X1 is the leakage reactance of the primary winding, and I1 is the primary input current, and I0 is the no load current of the transformer, and this will have the two components, one is Im, the other is IC, and IC will flow through the coreloss resistance R0, whereas the Im flows through the coreloss magnetizing reactance X0, and I0 is the vector sum of IW and Im, and here the current primary current called I1 dash, and this I1 dash is corresponding to the secondary load current called I2, and N1 is the number of turns on the primary winding, and E1 is the induced EMF in the primary winding, and N2 is the number of turns on the secondary winding, and E2 is the induced EMF in the secondary winding, R2 is the resistance of the secondary winding, and X2 is the leakage reactance of the secondary winding, and load, it is a general load connected, and the voltage across the load is called V2. And now the present case is if the reactance and resistance of the windings are neglected, then we call leakage impedance is neglected. That is X1, X2, R1, R2 are negligible. In that case, this circuit is redrawn as shown below. That is like this. So here no R1, X1 business. Similarly, there is no R2, X2. Means just we short circuited that. Once that is done, so we find here the primary applied voltage is V1 or VP, and input current is I1 or IP, and the no load current is I0, and I1 dash is the primary current component corresponding to the secondary current I2, and remaining terminologies as usual discussed earlier. So now to explain it better, so let us draw that equivalent circuit in the form of the windings connected on the magnetic core. That is equivalent circuit of the transformer when X1 is equal to X2 is equal to R1 is equal to R2 is equal to 0. Under that condition, we draw the diagram like this. So here this is the primary winding connected to the AC supply called V1, and the input current to the primary winding is I1, and I0 is the no load current of the transformer, and E1 is the induced EMF in the primary winding, N1 is the number of turns on the primary winding, and I1 dash is the current corresponding to the secondary current I2, and E2 is the induced EMF, and N2 is the number of turns on the secondary, and V2 is the terminal voltage of the load. When the applied voltage V1 is there for the primary winding, then this produces a no load current. It takes no load current called I0, and that produces a flux called phi in the iron core or magnetic core, and this flux links with the primary winding and also secondary winding, and in the primary winding the induced EMF is called E1, which will be equal to N1 into d phi by dt, and similarly induced EMF in the secondary winding we call it E2, that is equal to N2 into d phi by dt, and because of this E2 and the load connection here, so current flows through the load I2, and this current is called the secondary current I2, and because of this secondary current, a flux is produced in the magnetic core called phi 2, but it opposes the main flux phi like this. So when the secondary current is not there, the current drawn by the primary winding we call as I1, that is equal to V1 minus E1 divided by inherent impedance of primary winding. So once the secondary is connected, means closed with the load, then the current flows, that is called I2. That current will produce a flux called phi 2, and this phi 2 opposes the main flux called phi, so that the flux linking with the primary reduces, so that E1 also reduces. In that case, the current drawn by the primary winding is I1 is becomes like this: E1 V1 minus E1 divided by inherent Z. So this value increases to I1 dash, because E1 reduces means this numerator increases. Once numerator increases, I1 value also increases. So that value we call as I1 dash. And this I1 dash, called the primary current component, which brings the flux to the normal value phi, so that this flux induces or brings the E1 to the normal level. So to get this, the primary ampere turns must be equal to the secondary ampere turns, that is I1 dash into N1 is equal to I2 into N2. Because the I1 dash and N1 opposes the I2 N2, so we get here minus sign. So since the flux is established to the normal value, means this device is called constant flux device or constant flux transformer. Under this load conditions, we write the input current to the transformer primary as I1 is equal to I0 plus I1 dash. So the vector sum of I0 and I1 dash is nothing but I1. And this I1 dash can be calculated using the MMF formula, that is I1 dash into N1 is equal to minus I2 N2 is equal to, so that can be written like this: I1 dash is equal to minus I2 N2 by N1. So this I1 dash vectorially opposes the vector I2. Once this process is known, now we can take the nature of the load into account to draw the vector diagram of the transformer. Suppose the load connected to the secondary winding is pure resistive. In that case, the vector diagram will become like this. The applied voltage to the primary is Vp, and the primary will take the current called I0. That I0 produces a flux in the core called phi that will lag the applied voltage Vp by 90 degrees like this, and this flux induces primary EMF and also secondary EMF. Primary EMF is called EP or E1. Secondary induced EMF we call as E2, and these induced EMFs will lag the flux by 90 degrees like this. And since the load connected is resistive load, so and circuit secondary is closed, so secondary current will flow through the load. So that current is called IS, and that current will be in phase with the secondary induced voltage like this, because there is no voltage drop in the winding, as we assumed the leakage impedance of the transformer is 0. So IS is in phase with ES. But this IS, as we discussed earlier, will oppose the main flux, so that the primary current produced in the primary winding is called IP dash, that will oppose the IS like this. So the calculation of I1 dash or IP dash is already covered in the form of equation, that is I1 dash into N1 is equal to I2 into N2. So from that we calculate what is I1 dash or IP dash. Once that vector is known and I0 is known, then we can draw the resultant vector called IP. This is also called I1 or the net input current to the primary winding. Now, the angle between I0 and the applied voltage Vp or V1 is called the no-load power factor angle, whereas the angle between Ip or I1 and the applied voltage Vp or V1 is called the transformer power factor angle. And next, coming to the another load, suppose the load connected to the secondary winding is inductive load, that is RL load. In that case, the procedure is like this. The applied voltage to the transformer primary is Vp or V1, and the transformer will take the no load current called I0 like this. This I0 produces the flux in the core called phi, and this flux lags the applied voltage Vp or V1 by 90 degrees like this, and this flux induces EMFs in the primary winding and secondary winding, and they will lag the flux by 90 degrees like this. One is EP, the other is ES. ES is the induced EMF in the secondary winding, whereas the EP is the induced EMF in the primary winding. EP is also called E1 and ES is also called E2. And since we are assuming here inductive load, that is RL load, so the current flowing in the secondary winding will lag the secondary induced EMF by an angle called phi s like this. And once Is is known, there will be definitely a opposing current in the primary winding, that is called the I1 dash or IP dash like this, and calculation of IP dash is already covered. And having known this IP dash and or I1 dash and I0, we can calculate the resultant of IP dash and I0 to get I1 or IP, that is like this. Once IP or I1 is known, the angle between IP and the applied voltage Vp or V1 and I1 is called the power factor angle of the transformer, that is phi p. Similarly, the angle between I0 and Vp is called the no load power factor angle. Similarly, the same procedure if we apply to the capacitive load, that is RC load, the vector diagram will become like this. The applied voltage to the primary winding is Vp, and the no load current drawn by the primary winding is called I0 like this, and this I0 produces flux in the core, and this will lag the applied voltage Vp or V1 by 90 degrees like this, and this flux produces flux induced EMF in the primary and secondary like this, EP or E1 in the primary, and whereas ES in the secondary winding, this is also called E2, and this EP and ES or E1 and E2 will lag the flux by 90 degrees like this. Because the load connected here is capacitive load, RC load, the current flowing I2 or IS in the secondary winding will lead the ES by some angle called phi s like this. Once secondary current is there, then automatically there should be a opposite current in the primary winding, that is called IP dash or I1 dash, and the calculation of I1 dash is already covered. And having known the I0 and I1 dash or IP dash, the resultant current can be calculated, that is IP, and this IP is nothing but the primary input current. This is also called I1. Now the angle between this IP and Vp or V1 and I1 is called the transformer power factor angle, whereas the angle between I0 and Vp is called the no load power factor angle, and the angle between Is and Es is nothing but phi s.